Imagine trying to manage a team of satellites, hundreds of miles above Earth, all working together in this incredibly delicate dance. How in the world do you know if one of them starts to, well, go rogue? Today, we're diving into some really fascinating new research that offers a super clever solution for keeping these high-tech swarms in perfect working order.
So the whole idea of satellite swarms, it doesn't just come from an engineering textbook. It's actually inspired by nature. Things like flocks of birds or schools of fish. This idea of biological cooperation, that's the real foundation for the advanced systems we're talking about today.
And this slide lays out a fantastic analogy. On one side, you've got a flock of birds. On the other, a swarm of satellites. Both are trying to achieve goals that a single member just couldn't handle on its own, right? They both use cooperation and shared information to get the job done. In the world of engineering, we call both of these multi-agent systems.
Okay, so let's get a really clear definition here. A multi-agent system, or MAS for short, is basically a team of independent players. And it doesn't matter if they're birds or robots or satellites. The key is they communicate and coordinate to tackle a mission that's just too big for any single one of them to do alone. So, we have this really elegant concept, and it's all inspired by nature. But what happens when things go wrong? This is where we get to the tough, real-world problems these systems face. Because, let's be honest, every complex system has a potential weak spot.
So in a perfect world, the ultimate goal for any of these satellite swarms is to achieve something called consensus. It's basically a state of perfect agreement. Every single satellite is on the same page, they share the same goal, and they're all moving together like one cohesive unit.
And that brings us to the million-dollar question. What happens when that harmony is broken? When a single satellite in this super intricate network just stops playing by the rules. And here's where it gets really dangerous. See, because all the satellites are connected, a problem in one doesn't just stay in one. It can spread like a virus through the communication links, confusing its neighbors, and, well, it could potentially bring the entire mission to a grinding halt. So obviously, engineers need a system to fix this. It's a process called fault diagnosis, and it breaks down into 3 key steps. First, you just detect that something is wrong. Second, you have to isolate where and when the problem happened. And finally, you identify exactly what the fault is and, how bad it is. Now, this really highlights what makes this so difficult. The diagnostic system has to be incredibly smart. It has to be able to tell the difference between external disturbances, think of it like random static from the environment, and a genuine system fault, which is an actual broken part. It has to filter out all that noise to find the real problem. And this is exactly where the new research comes into play. A couple of researchers, Barzegar and Rahimi, have proposed a really innovative solution that tackles this problem head-on. So their method is built around something called an unknown input observer, or UIO. I know, it sounds super technical, right? But think of it like a really, really smart filter. It has a mathematical model of how the satellite should be behaving. By comparing that model to what the satellite is actually doing, it can tell the difference between predictable noise and the unpredictable signal of a real fault. It basically just tunes out all the static. And this new approach, it's a total game changer. For one, it works even if the satellites in the swarm aren't all identical. It also integrates diagnosis right into the control system, which makes everything way more efficient. But honestly, the most impressive part, it allows a single satellite to diagnose problems in its neighbors. This drastically cuts down on the computational power and the cost needed to keep the whole swarm healthy. Okay, that all sounds great in theory, but the researchers had to prove it, right? So they put their method to the test in a pretty detailed simulation. For their simulation, they created a virtual network. And in that network were 7 small satellites. Now, to make the test really challenging, they split these 7 satellites into 2 separate clusters, just like you see here. And each cluster was given different tasks and had to operate under different environmental conditions. So a really realistic test. And here is the crucial twist in the whole experiment. They didn't give this diagnostic tool to every satellite. Nope. They installed their unknown input observer on just one satellite, Satellite 7. The big challenge was to see if this single satellite could act as the doctor for the entire swarm. So, what did they do next? They broke things on purpose. They simulated a fault in an actuator on Satellite 2, that's in the first cluster, and then they simulated another fault in Satellite 4, which is over in the second cluster. The big question was,
Could Satellite 7 see both of these problems from all the way over there? The results were, well, they were pretty remarkable. The single observer on Satellite 7 had a 100% success rate. It perfectly detected and accurately estimated both faults, the one in Satellite 2 and the one in Satellite 4, even though they were in totally different clusters. The system just worked flawlessly. And this quote from the research paper, it just sums up the breakthrough perfectly. One observer was able to diagnose faults across cluster boundaries. When you think about these huge mega constellations of satellites, this is a massive leap forward. It's going to save an incredible amount of computational power, energy, and of course, money. So what's the big picture takeaway here? I mean, why does creating a more efficient diagnostic tool for satellites actually matter to the rest of us? Well, because this isn't just about satellites. These same principles apply to any multi-agent system. We're talking more reliable internet from those mega constellations, safer drone deliveries, more efficient convoys of self-driving trucks on the highway, and even more robust teams of robots in factories or, heck, even exploring other planets.
This research is a really critical step forward, especially as we enter this new age of intelligent, cooperative machines. And it leaves us with a huge question for the future. As these swarms get more and more powerful and autonomous, how do we make absolutely sure they're not just smart, but that they're also fundamentally resilient and trustworthy?